So far, we've talked about what a register interference graph is and defined the notion of graph coloring, but we haven't actually talked about how to compute graph coloring. So that's the next issue that we have to deal with. And unfortunately, it isn't easy. So graph coloring is a very hard problem. If you had a computer science theory class, then it will mean something to you when I say that it's an NP-hard problem to compute a coloring of a graph. If you have not heard about NP hardness before, that's not a problem. The important thing is that nobody knows an efficient algorithm for this problem, so there's no fast procedure known. And so the solution that we will talk about, the one that every compiler uses, is to use some heuristics, or basically approximation techniques that don't solve the problem completely. But there's a second problem, which is that a coloring might not even exist for a given number of registers. It might be that we only have 8 registers on our machine and there is no coloring of the graph that uses fewer than, say, 9 or 10 colors. And so we're going to have a way to deal with that. And we'll talk about that later. I won't say anything more about the solution to that problem just now. So now I'll present the most popular heuristic for coloring register interference graphs. And the basic idea is very, very simple. So what we'll do is we'll pick a node, T, that has fewer than k neighbors in the register interference graph. Okay, and this is actually the key thing. So just find any node in the graph that has fewer than k neighbors. And then we'll eliminate T and its edges from the register interference graph. So we'll just delete that node and all the edges adjacent to it. And then if the resulting subgraph is k-colorable, then so is the original graph. So the idea here is to do a divide and conquer kind of approach. We pick one node, we delete it from the graph, we color the remainder of the graph. Okay, it's a smaller problem with one fewer nodes. And then when we're done with that, I claim that we can find a coloring for the original graph. And why is that? Well, let's draw a picture here. So let's say we have a node that has fewer than k neighbors. And let's just say, for the sake of argument, that it has 2 neighbors. And here's the rest of the graph. So this big circle is the rest of the graph. Here's the node T that we're going to delete. And let's say that it just has 2 neighbors. Okay, so now what we're going to do is we're going to delete T from the graph, and then we're going to color the subgraph. And let's say that we succeed in coloring the subgraph. So we now have a coloring for this big ball in red, and now we want to construct a coloring for that big ball plus this node T. Well, since we said there are fewer than k colors needed to color the subgraph, and that 2 is certainly less than k, well, then there must be a leftover color for T. So we can look at all the colors of the nodes that are adjacent to T. Since there are fewer than k of these, they can't use all k of the colors, and then we can pick one of the leftover colors for T. So here's a procedure that works very well in practice. First, we pick a node T that has fewer than k neighbors. We put T on a stack and remove it from the register interference graph, and then we recurse. We repeat this procedure until the graph is empty. So we just keep choosing nodes that have fewer than k neighbors, pushing them onto a stack and deleting them from the graph. And we do that until the graph is completely emptied out. And that's the first phase. So that's part 1. Okay? And then in part 2, we assign a coloring. We build a coloring for the nodes on the stack. And the nodes are processed in the reverse order they were added. So the last node added to the stack is processed first. And at each step, what we do is we pick a color that is different from those assigned to the already colored neighbors. So the idea is we pick a node off the stack, we pop it off the stack, we add it back into the graph along with the edges that it had in the original graph, and then we color it. So then we look at its neighbors. Since we had fewer than k neighbors at the time it was deleted, it will have fewer than k at the time it's added back in. There will be a color available for it. We color it, and then we repeat by picking another node from the stack, and we do that until all the nodes of the graph have been processed. So let's do an example. Here's our register interference graph. So we're going to process this rig with k equal to 4. So initially we have the entire register interference graph, and the stack is empty. All right, so the first step is to pick some node that has fewer than 4 neighbors. So let's pick A, since it only has 2 neighbors. So what do? We delete A from the graph and we push it onto the stack. So after that step, our graph, here's our graph with A removed, and here's our stack. All right, now we're going to pick another node that has fewer than k neighbors, and if we look, fewer than 4 neighbors. And if we look at this graph, we can see that we have the option of picking a few different nodes. We could pick D, or B. Actually, there's only two different nodes we could pick because C, E, and F all have 4 neighbors. So let's remove D, arbitrary choice here, doesn't matter which one we pick. And now the stack will have D and A on it, and our graph will be down to these 4 nodes. And now something interesting to observe here is that all the nodes at this point have fewer than 4 neighbors. And so since every node in the graph has fewer neighbors than the number of colors we're allowed to use, at this point the graph coloring is guaranteed to succeed because every time we remove a node, we can only reduce the number of neighbors of every other node in the graph. It's also interesting to note that even though some of the nodes had 4 neighbors in the previous step, and so might not have been colorable, we couldn't choose them at that step because potentially a coloring of the neighbors would use up all the colors. Notice that now they all have fewer than 4 neighbors, and this is one of the interesting properties, or one of the good properties of this graph coloring heuristic, is that even if a node has many more than k neighbors, eventually we may remove enough nodes from the graph that its number of neighbors will drop below the number of colors available, and then we'll be able to color it. So anyway, now it doesn't matter which node we pick because we can process them in any order at this point. We'll remove C from the graph, and we wind up with this graph. And now picking another node, we can remove B. Now we're down to just a 2-node graph. Let's pick E and remove it from the graph. Now we're down to just a 1-node graph, and we move F from the graph. And now the graph is empty, and we have our stack. And notice that the stack, all we've really done in this procedure, the goal of this first phase of the procedure has been to put an order on the nodes of the graph. This is the order in which we should assign colors to the nodes of the graph. All right, so now working backwards, after we're done with the first part, now we got to do the second part where we actually assign the colors. And we're going to begin with the top of the stack. So we'll take node F and put it back into the graph, and we'll assign it a color. And let's just say we're going to pick the lowest numbered register that is not used by any of its neighbors. And so since F is in the graph by itself, we'll just assign it register 1. Now we add E back into the graph, and it has to have a different register from F. And so since F is using register R1, we'll just assign E register R2. Now we add B back into the graph. It has to have a different color or register than both F and E, so we'll assign it register R3. We assign C back into the graph. Now notice that C has all of F, E, and B as neighbors. They're using the first 3 registers, so C will get assigned register R4. And now we're out of registers. These 4 nodes are using all of the registers. But because we deleted things in the right order in the first phase, we know that when we add in other nodes, the rest of the nodes on the stack, they won't have all of those nodes as neighbors. So there'll be some register available to assign. So looking at register D, looking at node D here, it has as its neighbors F, E, and C. And so the only register that it can be assigned is R3, which is the same register as B. This is the only register that isn't used by one of its neighbors. Okay, so D gets assigned register R3. And then we assign we add A back into the graph, and we look at its neighbors, and they're using registers R1 and R4. So A could be assigned either register R2 or R3, and since our rule is just to use the lowest numbered register that isn't used by one of the neighbors, we'll assign it register R2. And there's our complete coloring of the graph.